are really, really important, not only in physical chemistry, but also for physical chemistry. Because surfaces are very, very much different than the bulk. And as a consequence, we need to understand surfaces so that we can understand how materials react. It's kind of trivial how important surfaces are. We all know each other by our surfaces. I see your surfaces, I don't see your insides. So clearly, all your outside, your surface defines you for me. And the same thing is in substances, in other substances. And you are not bound terminally. You look different on your surface than you look on your inside. And so is that also the case for anything and everything that you have. So there's not only that a very thin membrane can make a different surface to the inside of it than to the outside. Even if I have a beaker of water or a beaker of a liquid and I have the surface of that liquid, that surface will be fundamentally different in its chemical composition, in its structure, in its properties than the bulk of that liquid. And then surfaces have mechanical properties which give rise to shapes like you have them over here, much different than what you expect from the volume phase of a material. So it's important to understand surfaces. There are a couple of additional reasons for that. If I think about heterogeneous reactions, much of bulk and commodity chemistry is all about heterogeneous reactions, then those heterogeneous reactions really take place at the surface between the phases. And so it is good to understand what the surface of biological systems I talked about here already. Then there are lots of technological places where surfaces are relevant, and where chemists provide insight into how to protect, how to modify these surfaces: lubrication, corrosion, adhesion, detergency, electrochemistry. All of that has to do with surfaces and the structure of surfaces. And so it's important to understand that. And then there are materials, we'll talk about that at the end of this class, which are basically only surface. Some of those materials are at the research focus in my lab, and if you look, say, at Patricia over there, who's working in my lab, she's making materials which just consist of surfaces and looks at how those materials behave in a separate way. In other materials like foams, soaps, gels, and so on, have lots and lots of surface area. And making them have a lot of surface area is important for the application. And so again, we need to understand surfaces to see what's going on. The words surface and interface are really interchangeable. If you talk about interface, you really think maybe a little bit more about that there are two phases and the interface is between them, whereas if you talk about the surface, then you say, oh, there's only one interesting thing, and that has a surface, and then there's nothing about it. But that is really a matter of perception only. That is not a matter of reality. So there's always something on the other side, even for a vacuum. And even if it's vacuum, it will affect how the material behaves here at the surface. It is relevant. Now, the phases can be different phases of the same material. An ice cube and water, it's water on both sides, but it is still the surface of the ice in the water. There are different phases of the same material, or it could be something else, different materials. Surfaces started to be studied about 150 years ago when thermodynamics emerged. That was a time when people started building steam engines, and I believe the development of steam engines and the way that people tried to figure out how much power can they get out of a steam engine, how is the heat being transported formed into work, and how much work can you get, make people sensitive to the fact that they need to understand how much work there is really with systems. And so they studied it precisely, and they realized that if I had the surface here in the cylinder and the piston might be moving over here and increase the surface area or decrease that surface area, there's actually an energy component to that. So surfaces have a surface tension. And the word is called tension because if you were to pull out this piston over here, then the surface, the need to make extra surface would restrain the piston from going out, and it would kind of be like on a rubber string which has tension. The surface pulls against the piston. And for that reason, people say it's a surface tension, something which keeps the surface tight over here. But really, of course, we have to think about in terms of energy. Really, we have to think about this interface, this surface over here, making that costs energy. And if making that costs energy, then there's a certain energy per surface area which we have to expect. So surface tension, even though it's called tension, like electromotive force is called force, and neither of them really are forces, they are all energy per something. And so surface tension is energy per surface area made. Now where does this energy go to? If I have a material and I have interface between it, then really at the interface, it's rarely the case that you have a pure material here and a pure material there, and all the material is all the same up to the very interface, and all this material is all the same up to this very interface. Usually there is an interfacial area over here where the properties of the material are different. And it is even the case if alpha were vacuum. Then even if alpha were vacuum, then the properties of this only one material which is present over here will change as the material approaches that interface. One way of viewing that is if I have an atom or molecule of a species and it comes close to surface. At the surface, it's missing nearest neighbors to take to interact with, whether it's polar interactions, or van der Waals interaction, or whatever interaction, metallic bonding, it might be a covalent network solid over here. Whatever the interactions are here, there will be less partners to interact with at an interface, at least less partners of the same species than in the bulk. And the material will respond to that, respond to it by maybe having a fuzzy interface over here, and then having a smaller effective density, or by contracting into interface, so that these molecules over here, which are missing nearest neighbors going up, sit a little bit tighter laterally over there, and then we have a higher density at the interface. You all know material which does it, gold. If you have the surface of gold, and you have a really clean surface of gold, and at the surface of that gold, the atoms are sitting tighter than in the bulk. The gold is an FCC metal, and we have the FCC arrangement of the atoms in it. Just at the surface layer, there is every 20 atoms or so, there is an extra atom in there, so that they are not anymore in the FCC lattice. Gold is reconstructed to have more atoms at the surface in order to provide that temperature. Now, if we think about surfaces then and surface tension, then we find that it's very frequently measured in dyne per centimeter. Looks like per centimeter, but really it is still the unit of per centimeter squared. It's just divided how to divide it out. So a dyne per centimeter is an erg per centimeter square, or just a millijoule per square meter. And that what really is ideal. Luckily, these CGS units map nicely on the millijoule per square meter, or millinewton per meter. Surface tension for water would be on the order of 70 of that. If we have materials which have high surface tension, like mercury, it would be on the order of 50. Surface tension, of course, very much depending on the temperature before you come back. You all know surface tension in action. You know water striders run on a surface of a lake because there is unfavorable interaction between the legs and the liquid. If the leg were to move into the water surface, or the foot would move into the water, then there would be water molecules which now have to interact with the feet of the water strider rather than with other water molecules, and that would be energetically unfavorable, meaning the surface tension rather supports the whole water strider above the surface of the water than paying the energetic penalty of having interaction over here. Likewise, you can try to make some heavy objects float even on water if you oil a little bit. A paper clip is so that's hydrophobic, then you will be able to float even on water a paper clip, just because if you make the surface the hydrophobic of the paper clip, it would cost more energy to submerge the paper clip in the water, preventing strong hydrogen bridge bonds between the water molecules, because now they have to interact with the paper clip if it were inside the water, and so it's better to support. You can also see in lotus leaves or so that water is then walled up because the water molecules want to interact with other water molecules rather than with the leaf, because the leaf is so hydrophobic. So in order to understand surface tensions, we first have to realize there's surface tensions everywhere. So if I have a liquid on a substrate, then there is some surface tension between the liquid and the substrate. There's some surface tension between the liquid and the air, and there is some surface tension between the substrate in the air and the air. And in all of that, the material tries to find a balance of minimum energy. And so, if the interaction here is more favorable with the substrate, then the drop of the material will spread out to the side, and you will find that you have contact angles which are smaller than 90 degrees. Whereas what we saw a moment ago over here, we'll have contact angles. If I were to look at the contact angle here underneath, then the contact angle would be not larger than 90 degrees. It is less favorable to interact in that fashion. So looking at the contact angle, measuring in a microscope, these kind of angles over here allows you direct access to the surface tension. So measuring contact angles between drops can give you information about surface tension, and as a consequence, it can give you information about intermolecular interaction in the material and with the substrate, which otherwise would be hard to obtain. If you think about a water-repellent fabric, they work just the same kind of way. There's a high surface tension, costs a lot of interfacial energy to make a surface between a liquid, water, and a material, and as a consequence, you have a very large contact angle. As a consequence, you have very large spheres of the liquid on those materials, and you can have pores in them even without liquid being able to permeate through them. Now, from a thermodynamic perspective, that's a real big problem, surface tension. Because if you were to imagine you have a setup like this, you have like a conical shaped object, and in your conical shaped container, you have the tube in the bottom over here, and you have the tube in the top over here. And those two liquids over here, they might have a high surface tension between each other. They don't mix, they form an interface. what kind of interface will form? It will always be something near spherical, the interface. Because being near spherical, a sphere contains the most material at the least surface. So having a rounder spherical interface over here makes the surface area the smallest, and as a consequence, the energy expended to make that surface area small. Okay. If it's really big, then gravity might be prohibitive for that, but if it's really small, then gravity is not so important, and you'll have something round. Now, if there is something round in here, if there's this round surface in here, and the round surface costs energy, then there's a driving force for that surface to go in the inside. Go down over here, become smaller, because if it were going down, then we would have less surface area. So the surface over here compresses the phase alpha over here and expands the phase beta, which means that now between the phase alpha and the phase beta over here, I have different pressures. This is something from a thermodynamic perspective which really should not happen, because I have two phases which can do volume exchange. They should equilibrate the intensive property which is associated with volume. They should equilibrate the pressure, but that is not the case. There is pressure here and there's pressure there. The pressure over here is higher than the pressure over there, just because of the indifference. And you can calculate the difference of that and the inside minus the outside pressure is given by 2 times the surface tension, this number of how many joules it costs to make a square meter, divided by the radius of this one. So the smaller the radius r is, the higher the difference in pressure. So surface tension plays the more a role, the more we go to small particles. So if I were to look at a water drop of 1 centimeter, a little bit less than half an inch, about this size or so, then the difference between inside and outside would be 0.1 hectopascal or 0.1 millibar. If I had a really small water mist particle, then the difference is already 10 hectopascal. That is, 10 hectopascal is the difference which makes a strong wind already. That is, in the atmosphere, reasonable. You don't get much higher differences in the atmosphere, at least under normal conditions. In a tornado maybe, but otherwise you get not much bigger difference in the atmosphere like that. And you have achieved just different sizes of drops. We also right now hear a lot about the SARS virus. And the virus is a very small particle having a capsid, having a membrane on top of it. And that membrane, of course, has a surface tension. It costs energy to make a membrane surface. And our cells are much bigger objects. And the infection of the virus, there are lots of biological reasons why the virus infects us. But there's also a very simple physical reason. And that is that the virus is maybe 1/10 of a micron in size. Our cells are maybe 1 micron in size. There's an order of magnitude difference between them. And they are all very small in this regime where it's getting smaller and smaller, and the pressures are getting higher and higher. So the inside of the virus is at a much higher pressure than the inside of our cells, allowing the virus to transfer its information into our cell. Now, how it does it? Lots of biochemistry. But the driving force behind it is nothing else than just the surface tension, which we're talking about today. There's capillarity as well, and capillary rise and capillary depression. And that again has to do with surfaces. If the fluid, if the liquid does not like to interact with the surface of a capillary, then it will try to minimize the surface area it has over here and try to rather increase its surface, which is just the pure liquid surface, and you'll have capillary depression. The material is lower in the capillary. In the opposite, if the interaction is favorable between the liquid and the capillary surface, then you have capillary rise. The material will rise up in the capillary, going up above the level of the liquid. This capillary rise is driven by the attractiveness of the interaction between the material and the tube wall. So capillary rise, if you see capillary rise, if you see wicking, or if you see that something soaks up something, it is all driven by surface interaction, by favorable, energetically favorable interaction between the liquid and the solid object compared to just liquid-liquid interactions. And then you can use the capillary rise in order to figure out how strong those interactions are, what the surface tension of the material is. There is quite a bit of temperature dependence in them. Where would you expect no surface tension anymore? The surface tension vanishes at the critical point. At the critical point, I don't have a distinction anymore between a liquid and a gas. They are both the same. There's no distinction there. So, if I know that at the critical temperature I have no surface tension anymore, then it is a reasonable assumption that the surface tension you have depends on how far are you away from the critical temperature. So if you take temperature divided by critical temperature, if you were just at the critical temperature, then it's 1 minus 1, the whole thing goes away. And as you are at lower temperatures than the critical temperature, you'll have more and more surface tension in the material. And Guggenheim suggested this formula with the power of 11 nines. It is not a very precise way of doing science, in the sense that you look through many different materials and you find what is the surface tension as a function of temperature, and then you make curves for these surface tensions. You see they all behave a little bit different. And then you try what is the formula that best fits all those different kinds of curves which you can tabulate. Then 11 nines turned out to be a little bit better fit than just 1 over there. But the whole point is not that this is a super precise formula, but that it gives you at least an idea of how to think about the surface tension and where to think that the surface tension will stop at the critical. Now, there are supercritical fluids, and you all have used, in a way, supercritical fluids. Every single time you go to the dry cleaner, you use supercritical fluids. The dry cleaner is dry because the dry cleaner uses fluids which are supercritical, which don't have, wet in that sense, they don't have surfaces anymore. They are above the critical point over here, and you're closing a clean in that way. Now, supercritical fluids are used at many places. In chemical catalysis, they become more and more important because the presence of the surface and the presence of the liquid as distinct from a gas is unfavorable for many processes. If you want to have, for instance, separation, you are in a supercritical phase, you are over here, then separation is really easy because you can just reduce the pressure, and if you're somewhere over here, you reduce the pressure, your solvent becomes gas, and you're left with the solid which you had in the supercritical phase. So separation is really easy. Also, we just talked about surface tension. If I am in the liquid phase, if I'm in the phase over here, I have surface tension surrounding the liquid. And so the surface tension will make shapes, will form droplets, and that is often not favorable because the droplets makes material aggregate. If you want to have very fine powders, or if you want, for whatever reason, to prevent material from aggregating, you want to work with supercritical fluids because they don't have the surface tension, they don't provide aggregation of the material. We talked about the semiconductor industry a couple of sessions ago. Here again, supercritical fluids become important because if you have very fine features on a wafer, then the surface tension of just making them wet can be so strong that they make those features fall over. They break those surface features. If you make very fine comps or other vertical pillars on the substrate, surface tension can pull them over, but you don't have surface tension at all if you work with a supercritical fluid to clean them or to remove or to develop the material. And so more and more processes are done in the supercritical phase. So chemistry has a shift to wherever fine control is desired to be proceeding in the supercritical phase. Now, that is mostly Chem 1, what I'm saying right now. There are, of course, immiscible fluids, there are unfulfilling molecules, which bridge between, for instance, a polar and a non-polar phase. We've heard about them. Then in Chem 1, I hope, this is just a reminder, those unfulfilling molecules have ends which are polar and other ends which are non-polar, and so they can bridge between those two phases. That is the foundation of detergency. If you wash your dishes with a detergent, it's an unfulfilling molecule. It's a molecule which can interact with the non-polar phase, or really which has an end which is repelled from the polar phase and which is part of the polar phase. And so it can suspend non-polar molecules in the polar water phase of the dishwasher or wherever detergency is required. Just a reminder, I'm sure you know that anyway, you can one instruction will have told you. There is really only polar interaction. There is no such thing as non-polar interaction. There is maybe interaction between non-polar molecules, but the water molecules do that same interaction as well. The polar molecules do the same interaction as well. It's just that the polar molecules, in addition to all the non-polar, van der Waals, London dispersion, whatever you want to call them, interactions, can also do polar interactions. And so the polar molecules are always the actors which define how phases are set, because they have another way of doing strong interaction, and they will repel out of them the non-polar molecules. But it's always the polar molecules which are the actors, which are the doing things, and not the non-polar molecules. Because polar molecules can also do non-polar interactions. It's just that the polar interactions are so much stronger that the non-polar interactions are usually glossed over. But they exist, of course, as well. If you have amphiphilic molecules and you offer them only one phase, then they will form a phase on top of the polar phase, like you have these amphiphilic molecules here on top of the water surface. And you can generate a film like that. That was one of the first ways of doing really atomic scale or single molecule scale science. If you were to take some amphiphilic molecule and pour them on the liquid, you'll make a layer on that polar liquid, which is just a single molecule thing. And those layers are visible with the naked eye because they reflect the light in a different way. Benjamin Franklin is credited, whether it's true or not, of putting some amphiphilic molecules on the pond. in its state, and that way measuring how big is the molecule by seeing how much, which fraction of his ponds, how much surface area of his pond he could cover with a specific amount of those hydrofluoric molecules. You can measure the size of them. And over the last 20, 25 years, it has become a more and more common practice to coat materials just with a single layer of molecules in this fashion. You then talk about a Langer logic film, which is the film which you pick up from the surface of a water phase. So if you were to dunk something into the liquid phase and pull it back out, you would create one or two layers, one layer going down, another layer going up again of those unfulfilled molecules on the surface of whatever you move. If you want to have a single atomic layer coverage of an object, that is the way to go. And there's lots of research done in using such kind of techniques in analytical chemistry. Jason Chem, for instance, is doing quite a bit of work in that field. Colloids are an old name in a way that before the hype was nano, which means dwarf, nano, then before that in the 60s and 70s of the last century, everybody was talking about colloids and colloid science as the science of small objects, realizing that small objects have different properties than large ones, and crediting much of their difference in property to the abundance of surface in these materials. There was the same time when smog became important, for instance, in Los Angeles and other places, because cars became so unlike London. And the smog is nothing else than a colloid suspension, a suspension of mostly solid particles in air. So it's an aerosol. It is material which has an enormous amount of surface area, because they're tiny, tiny particles, each of which have their surface. And at this surface, chemistry takes place. And it's quite astonishing how different the chemistry at the surface of these particles is from both the chemistry you would expect in the bulk phase or in the gas phase of these materials, and also very much from the chemistry you would expect to occur. If you think about atmospheric chemistry, you think a great deal about chemistry precipitating on the surface of materials, on the surface of liquid or gases phases in the air. And the chemistry is outright weird. Jing-Sung Zhang in the chemistry department here is doing lots of research on that, and he usually has undergraduate researchers in his lab if you're interested in that. So he's working more on atmospheric, lower atmosphere particles. But even if you go into the higher atmosphere, the ozone hole, which like the Antarctic, also has to do with the surface chemistry of materials in stratospheric clouds. It doesn't happen just in the gas phase. Much of which we perceive as air pollution has to do with high surface area particles in the gas phase. It became also very apparent to us in our lab that in the reconstruction of renovation of piers, lots of asbestos was released, and we had problems in the lab with that. Again, it was a problem of something suspended heterogeneously, having a lot of surface in the air. Then other ways of looking at large surfaces are emulsions. The milk over here is not transparent because there are small fat particles in it, which have unfulfilled molecules surrounding them so that they can be suspended and their surface scatters light, and that is the reason why the milk is not clear. all the constituents in the milk. If they were just a homogeneous solution, milk would be clear. But what is not clear is the scattering on the surface of these heterogeneous particles, the fatty phases and the non-fatty phases, the polar phases and the non-polar phases. So if you think about having what paints, coats, coatings, whatever, whether they're clear or not depends on do they have internal surfaces that can scatter light or that can't scatter light. And that's the work of chemistry. The chemist is in designing such materials and ensuring the quality, and so understanding surfaces and seeing what impact surfaces can have is important. Another area where surfaces are really relevant are phones. If you have a phone, then the phone also has lots of surface. It's kind of the other way around, that really only the surface is there, and the inside you have the gas. But certainly these are colloids, certainly these are materials which are characterized by their surface. And with that, I think I'm done. What I want to say about surface today. The last thing I have over here is a homework which is based on what we did in the last week on transport. So I asked you over there that you have a beaker of different kinds of materials, and the beaker is sitting on top of the Bunsen burner. The Bunsen burner is providing a certain amount of heat distributed across the bottom surface of the beaker. And then you have to look at the heat conductivity of the bottom of that beaker in order to figure out how warm the bottom surface of that beaker is actually going to become. Not too difficult. And the last homework, and of course only bonus homework, because only the first round. There will be office hours the normal way this week. There will be no office hours next week because we have the exam on the month. Okay, if you still have anything which you want me to tell on Wednesday, day after tomorrow, please send me emails. Otherwise, I'll do some review and go a little bit about career advice. Thanks so much.